intervals of increase and decrease. So I've mapped out, I put them in pairs here, the reciprocal and its original function. So the very first one is just a normal linear line on a graph that goes through the origin. Whoops, I missed the origin. There you go. That's our first graph. And then the reciprocal of that is very similar. I'll show it on a graph very soon. Sorry, that was incorrect. It should be like this. The reciprocal of that function. So what we're going to do is how to calculate the intervals of increase and decrease. Well, what we want to know is what is the very first function doing? Is it increasing or decreasing? Because the coefficient in front of this is positive, that means we have an increasing function. Okay? And what that means for our reciprocal of it is the opposite. We actually have a decreasing function. So I'll use a negative and a down arrow. They both meaning the same thing. And what are we talking about when we talk about increase and decrease? Well, what that means, get our little arrows out. You can't see that far. There you go. We're always talking about starting at essentially negative infinity and heading towards positive infinity on the x-axis. Okay? So essentially what we are doing is we are heading, see if I get a nice, that'll be a good object to use. We're always starting here and heading in this direction. Okay? So when we're talking about the x, whether it's increasing or decreasing, we're talking about heading in a positive direction on x. What is y doing? And that's what we report on, is y increasing or decreasing. So we have our example over here, and we got lots of things happening. Let's see if I can get a little pen. Got a pen selected. Let's shrink that again. There we go. We have our linear one, so like we said, it's heading upwards. This is increasing. As our x values are increasing, the y values are increasing. But for our reciprocal function here, it's actually constantly heading downwards. And then from here, it's constantly heading downwards again, so it's actually decreasing the entire time. Okay, so that can be a bit confusing with our linear ones. Let me bring this out so I can erase. Yay, okay. The next one we want is the opposite of that. Let's talk about a negative linear function. So over here we know a negative linear function, we know that's essentially heading downwards. And according to what we said, what that should mean is this function, the reciprocal of that, should be heading upwards, doing the opposite. So let's essentially check them out. Here's our negative and here's the reciprocal of our negative. Let's get our, oh, wrong button. I gotta push this first. I'm partially learning as I go. Yay, okay. So here's our linear function. It's heading in a negative direction the whole time, so we got that checked off, we know that. But our reciprocal of that is actually constantly increasing, so it's heading in an increasing version there. It gets up to the vertical asymptote, and then on the other side of it, it is constantly increasing again. Okay, so that checks out. That rule seems to hold for all of our linear functions, okay? But the next thing we need to do is we need to figure out quadratic, and that's where this becomes a little more difficult. So we have our reciprocals. We have our original quadratic and the reciprocal of our quadratic, okay? So we need to figure out some things. I'm going to show you what the graph actually looks like, so turn these two off. Here's our original quadratic, so I have my x-intercepts here, and I have the vertex, which is actually going to be a really important point. And then we have the reciprocal. I've put those in as important points, mainly because what we're going to find is we have to do a bit of calculating with this information. So, our original quadratic, as you can see, it starts, because I have a positive coefficient here, okay? So it's actually starting by heading downwards. It hits the vertex and then starts hitting upwards. So at this axis of symmetry, it's in a decreasing to the left of that, and then it is increasing after that. Okay, that actually is really important for what we're doing with our reciprocal of that. Change the color.
Oh, I'm starting to get it now.
Okay, so our color, I know I can change colors. Yes, all right. So here's our reciprocal. It is now heading upwards, okay? And it is actually heading upwards all the way up, so the opposite of our quadratic up to the axis of symmetry, so it is positive there. Then at the axis of symmetry, remember, our quadratic changed, our reciprocal changes. It then starts heading downwards up to that vertical asymptote, and then again after the vertical asymptote, it continues in a downwards or negative decreasing. So always keep in mind that the relationship between, oh, that's the wrong one. I don't want to clear everything, so I'm not going to do anything about that. The relationship between the original and the reciprocal of that function is if the original is increasing, then the reciprocal must be decreasing at those points, and then vice versa. Now, the reason the quadratic's a little harder is because we actually have to go about calculating our vertex. That's the only one that's really that important for increasing, decreasing. Obviously, the vertical asymptotes play a part in our graphing, but in terms of whether it's increasing, decreasing, it's only that vertex that's important. So let's go back over here and figure out how we can do that. Let's go on the assumption that you kind of already know how to find your vertical asymptotes. We need to find the vertex. One of the ways to do that is to find the x-intercepts. Another way is to complete the square. Because it's unlikely that you kind of remember you're completing the square, what I'm going to do is I'm just going to build off knowledge you already have. So vertical asymptotes, let's work on that. We know that vertical asymptotes essentially are bottom of our graph. It just can never be equal to the idea of 0. Okay? Otherwise, it's an undefined graph. So what do? We set the original equal to 0. So we have 0 is equal to, thank you, virus definitions, x squared minus 3x minus 4. So we need to factor. Because this is an a value of 1, we can use like our sum and product factoring. It's a pretty simple one to factor. We need two values that are going to add up to -3, and those same two values need to multiply to -4. So we can go with factors here. Factors of -4, well, there's -2 and 2. They're not really going to pan out here. So let's go with 1 and 4. And one of them is going to have to be negative and one's going to have to be positive. So we have 1 and 4. We know they multiply. 1 and 4, yeah, a combination of that can give us -3. One of these has to be negative. And it turns out if the 4 is negative, then the addition is true. And if the 4 is negative down here, the multiplication is true. So that works out really nicely. So we're left with 0 is equal to x minus 4. I should write it in green here. So that's one of them, x minus 4. And x plus 1. Okay? And we already know that we then set these equal to 0, and they'll give us our vertical asymptotes, right? So x minus 4 equals 0, x plus 1 equals 0. That means x is equal or cannot equal positive 4, and x cannot equal -1. Great. Very important parts of graphing. Don't quite help increasing and decreasing yet, but this information is important because, and we'll show you on the graph again. There it is. Let's turn off that guy. What you'll notice, oh, I'm getting faster, that directly in between this value here and this value here is the axis of symmetry. Whoops, I didn't quite draw that right. There it is. Yay, is our axis of symmetry. So what we do is we use a little formula. We need the average between these two. And the formula is essentially the idea of the first x-intercept plus the second x-intercept divided by 2 will give you your AOS, your axis of symmetry. Okay, so we'll do that on the other page. That'll give us our axis of symmetry, and we know that's where everything's going to do its changing. Okay, so let's slide on over here. Our axis of symmetry. AOS is equal to one of the x-intercepts plus the other x-intercept divided by 2. Okay, well, we have them. One of them is 4, and the other one is -1. Add them together and divide by 2. That gives us 3/2. Perfect. So we have our fraction, which is essentially our x value of the vertex is the same as the axis of symmetry, is 3/2 or 1.5. So for our sake, we actually don't need the y value. It's not super important. But what it did tell us, and we know because, now obviously we looked at our graph before, but because this a value is positive, okay, we know that our general quadratic is decreasing to that x value point, that x value being 3/2. So when x is equal to 3/2, it is a decreasing function. And then after that, it is then a increasing function. Okay, so if that's the case, our reciprocal then has this value being the important value, x is equal to 3 over 2. We know we must be the opposite of that. Because it's decreasing here, our reciprocal must be increasing, so it must be positive or increasing up until x is equal to 3 over 2, and then it is decreasing after x is equal to 3 over 2. So we don't even have to graph it, we just have to get that really important point at the vertex. Once we know that, we know we're the opposite of whatever the original quadratic is, and then we can kind of make our expectations from there. Okay. Like general sketching, not sketchiness, but just sketching in general. Our vertical asymptotes are important values. So vertical asymptote, we said one was at -1, I believe. So, and then we have another vertical asymptote at the value of 4. And then our, I think it's called inflection point, I don't quite remember, is 3 over 2. Okay, and this is our essentially our vertex for the quadratic, right? If you wanted things to be positive or negative, so not increasing or decreasing, you know, you plug in some value here, like -2. You plug in some value, actually I should do it in green. If we're just looking for things being positive or negative, -2 is a good value to plug in because we know it's to the left of a vertical asymptote, and that'll tell you if it's positive or negative at that point. Another value between -1 and 4, something like 0, could be another good point to get a coordinate and find out if something is positive or negative. So let's say positive or negative. This will help us find positive or negative. And then something like 5, or any number you really want, 10, infinity, whatever, positive or negative. That'll help you do that. But in terms of increasing or decreasing, our coordinates aren't as important because we could get a positive coordinate or a negative coordinate and still be either increasing or decreasing. So that type of idea of positive and negatives aren't very important for increasing or decreasing. We are either, what color? We'll use blue for increasing. We are either increasing or decreasing to the left of this vertex, and then we are either increasing or decreasing to the right of that vertex, and our relation to the original quadratic is essentially what's going to tell us for the reciprocal. Okay, so in terms of a number line, getting coordinates around the vertical asymptotes is important, but really our vertex is the only thing that's going to change increasing or decreasing of our actual function.
But just
you were asking for plugging points in this, anything to the left of this is good, anything to the right, anything in between is nice, but a good one to be would be this vertex point. If you were to plug this 3 over 2, in terms of our general sketching, we know we have, you know, a vertical asymptote here. I'm going to kind of superimpose a graph here. Let's say we're increasing. We know at this specific point it changes. Increases, then the behavior decreases, and then decreases again. So this is a pretty critical point to have in terms of the reciprocal function. It really gives us a good idea. Otherwise, between these two vertical asymptotes, we're kind of just guessing where it changes. Maybe I change it at 0 and I say it starts coming down. We know because of quadratic, it's in the middle of the two vertical asymptotes, and this point in the middle, we know is kind of our inflection point when it's changing. So that's a pretty good one to have, right in between the two, because that's where things go from increasing down to decreasing. That will give us a better sketch in general.
all right.
Okay. So let's say we want to formally state our function. So f at x is, I didn't actually check this one. What the heck is it? It's increasing. Okay, so for our reciprocal, our function f at x, actually it wasn't called f at x. What the heck was our reciprocal called? K at x. Okay, so make sure we get this stated correctly because the reciprocal was called k at x. So k at x is increasing from negative infinity, so that's all the way left, to 3 over 2. Okay, or you could say when x is, it's technically less than, it's not at 3 over 2 because at 3 over 2 it's neither increasing or decreasing, it's neutral, it's essentially 0, the tangent slope to it there. So x is less than 3 over 2, and technically less than and equal to negative infinity. K is increasing to there, and k at x is decreasing from 3 over 2 again to positive infinity. So that's where you use a point and an infinite number, or you could say when x is greater than, oh, I wrote that wrong, less than and equal to infinity, not greater than, can't be greater than it, infinity, but greater than 3 over 2, but not equal to, because
Right.
again, at that point. But for our linear functions, so that was for the quadratic, for the linear function, it is the reciprocal here we said was decreasing, so the linear function for x is decreasing from negative infinity to positive infinity. And for the second one, so that was our g at x, so we'll call that our g at x function. And for our I at x, this reciprocal, I at x was, we said, is increasing from negative infinity to positive infinity. And there's different ways of like kind of writing it
So
out.
there isn't really one specific way.
Yeah, and for linear ones, because it doesn't change, it's going to be between infinities. But for quadratics, you're going to need a point. A point will need to be involved because it's from infinity to a point that it's either increasing or decreasing, and then again from that point to the negative or positive infinity that is again increasing or decreasing.
Okay.
So quadratics is where you have like a two different types of behaviors. Reciprocals to linear, it's just increasing the entire time or it's decreasing the entire time.